Não sei a altura.
Yeah, so I think the camera like this is Estou mais um bocadinho, não?
É sempre um bom luz. É sempre difícil.
O microfone vai ficar ligado.
Não fazer? Não faz.
Não sei, eu tenho que falar para ver se isso faz com ele.
Não, desliga o microfone, está porque não está ligado, que está bom. Eu se bem, eu prefiro ouvir.
Eu não ouvi.
Está só pegar e se eu ouvir.
Na primeira,
Isso é realmente interessante. Tens a mesma. E é mais frio.
guardei aquilo, mas eu já não estragado.
Okay, so Byron, can you still hear us?
Yep.
Okay. So, well, welcome back, everyone. It's my pleasure here to introduce Byron Wallace. So, for a talk on information retrieval for medical applications. So previously, Byron was at Brown University. From there, he moved to UT Austin. I think I've met him more or less around that time. And Byron is currently associate professor at Northeastern University, in the same college as Ricardo that you saw here yesterday. So Byron works on text mining and natural language processing, often with or in the context of applications related to health and to clinical decision making. He has very interesting work on different tasks related to this, like question answering over these types of data, textual document classification, information extraction, summarization. So this talk here is going to be covering some fundamental aspects related to these problems and also some of his more recent work. Okay, so Byron, thanks again for accepting our invitation, and well, let's welcome the speaker.
Thanks, everyone. Thank you very much for the kind introduction, and thanks for the invite. And let me, first apologize again for the unfortunate situation. I will say Lisbon has been a lovely place to isolate. So it's fun in that respect. But yeah, so I'm sorry I can't be there in person, but I'm glad I'm not infecting you all with COVID. So right, what I'm going to do today. Let me just make sure. Yeah. Okay. So what I'm going to try to do is I'm going to try to cover some sort of broad areas and, being data people, I guess. I'll do this through the lens of data sources that are relevant to medical IR and NLP with the hope that maybe this would be provide enough kind of context to get you perhaps started in this broad area. So that's kind of my aim. And this being a set of disclaimers, when I'm not talking about my own work, I will be not trying to give any sort of like exhaustive sampling or sort of review of work in the space. It's a large space, so I just want to put it out there. This will be a very biased sample of stuff that I present that I think is illustrative of work in this area. And I will, like any good academic, I will mostly be talking about my work, of course. But I guess I still hope that it provides you a sense of the kinds of work that's done in this space and how kind of IR and I guess language technologies in general really have the potential to do a lot of good in this area, at least in my view. And my last disclaimer is, I think I have a better excuse than usual if I come off as a little bit disorganized or rambly. I've been in a little bit of a fog this week with COVID. Not too bad, but I we'll see how this goes. But you'll forgive me, I hope, if I'm not as sharp as I maybe usually might be or think I am. All right, so those are my disclaimers. And so, like I said, the way that I'm going to structure this is talking about like these different sources of data and the kind of data sets, tasks, and aims that have or some of those data sets, tasks, and names associated with each. So I'll start with biomedical literature, which is just basically refers to the universe, the very large set of published, basically scientific literature, health-related literature that's out there, and for example, indexed on PubMed. Sorry. And then we'll talk about social media, where there's a lot of sort of work on at the intersection of doing kind of IR and NLP things with social media and health. And finally, I'll talk about a little bit about electronic health records. So we'll see kind of how far I get along here. I'll spend I think I'll spend the bulk of the time probably on this first category of biomedical literature, in part because that's where most of my work has been in this space. And also because I think there's like a lot of sort of low-hanging fruit here, like easy wins, where you can actually do stuff that really would be quite useful for people. So that's the plan. I'll start off here. Okay, so I guess the first thing you should know in this space, the first kind of resource that you should be aware of if you're not, is PubMed. So PubMed is, and it's really actually an interface on top of the Medline index of medical literature. And it's kind of like the go-to, it's not the only index, of course, but it's basically like the go-to index for biomedical literature. And here I'm just showing, it's maintained by the National Library of Medicine, and it sort of provides basic search functionality out of the box, right? So it indexes basically a bunch of journals, and it supports sort of Boolean queries, as you might anticipate. These can get quite complex. One of the things that I've kind of discovered accidentally working in this area is that there's sort of like a whole subgenre of papers where people will, in different areas, people will like develop these queries, which can be quite complex. This is actually not a super complex example I'm showing, and they'll like validate these queries on PubMed in terms of like retrieving some kind of literature, and they'll establish some sensitivity, specificity, or what have you, and they'll like publish a paper describing this query, and people will use it. So you'll see these, and this is kind of the sort of search that PubMed supports. Okay, the other thing that you should know about PubMed is that you can search using controlled vocabulary terms, and these are from MESH, which is short for medical subject headings. So this is nice because they normalize for variance, right? And so in other words, like, this can disambiguate different instances of the same underlying concept. MESH terms are manually applied by curators at the National Library of Medicine. So that's obviously a lot of work. There's been some effort to automate or semi-automate this, but my understanding is it's still mostly done manually. So I should also mention that MESH is a subset of the Unified Medical Language System, which is also maintained by the NLM and is an overarching kind of sprawling biomedical ontology. It's a really rich resource that if you work in this space, you'll certainly make use of. The other thing that I should mention is that it does provide similar article functionality. So you can kind of like say, oh, show me an article similar to this one, with the exception that the methods, if you sort of, I got curious, I hadn't looked for a while, and I was prepping this, and I was sort of looking in. If you look, you'll see that the technology they're using to do this is maybe like arguably a little bit dated. They're using this thing from '89, the classic kind of Sultan reference. I think on the other hand, that probably works pretty well, but arguably it's not sort of state of the art, I guess. And so in light of this, of course, people have been working for years now on trying to kind of build fancier stuff, I guess, on top of the article in PubMed, so that you might have better search tools, basically, for the biomedical literature. So there's a very outdated survey from over a decade ago now that reviewed some of these. So if you're interested in like a history of the work, you might check that out. Again, it's pretty dated, but it would give like sort of a good background. I'll just highlight a few recent efforts, not my work, that I'm familiar with or that I've seen. So there's this Thalia system, which tries to do some sort of semantic search. I think they have a demo you can play with, which tries to kind of use, more state-of-the-art stuff to facilitate, I guess, richer search over PubMed. So that's kind of like an effort that you might be interested in checking out. I guess even more recently, there's been this effort called Spike, which I think it seems pretty cool. I haven't played with it extensively, but they do have a demo, I think. And this I think the idea here is basically it's targeting really interactive search for power users. So the idea is that you can search over, you can do, I think, quite complex things. You can search over like sort of entities, and I think you can even specify kind of like relations. So yeah, so here it's showing some example queries. And it's cool because I think it also allows you to do some sort of extraction with these queries. So again, disclaimer here is I haven't played with it too much, but this seems like a cool direction that I've seen developed over the course of a few papers. So if you're interested in sort of search over the medical literature broadly, these might be good places to start in taking a look at. I'll feature this. I just thought it was cool. So if you look at their FAQ for Spike, they're like, listen, there's lots of search systems over PubMed. Why should you use this one? And they're like, well, because it's harder to use. So I enjoyed that. But I think the idea is that it's really targeting these kind of power users. That's the idea. Okay, so the last kind of thing I'll mention, just like PubMed adjacent, I guess, you'll probably be familiar with, or maybe not, but there's this COVID-19 thing that was assembled at the outset of COVID by mostly Allen AI people. And this is basically just a resource, like a subset, actually from Semantic Scholar, of articles that are, obviously related to COVID-19. So that is just something to be aware of in this space. All right, so I guess the sort of like data, like really obvious sources of data. I should mention, like I said, there are things like Embase other than PubMed, but PubMed is really the big player and its derivatives. I'll talk now a little bit about some tasks and specific corpora for those tasks in the space. So I guess like the big, the sort of one of the big things that you should be aware of, I guess, with respect to IR and biomedical literature specifically, are the TREC tasks. So these have been going for a long time now. You can check them out at trek-cds.org. And they run a bunch of like sort of information retrieval shared tasks. And there's a bunch of nice data from past years, obviously, that you can get your hands on. Another challenging, another sort of shared task thing is BioAsk. And so this is all about biomedical semantic indexing, roughly classification, and question answering. And so there's, again, I would just point you to these if you're interested in this sort of thing as places to look at sort of what people have done in the past. Here's an example where they're sort of putting together information retrieval, question answering, and summarization. And just to give you a sense of what this data is like, you're right. So they have participants responding to test questions with concepts, articles, snippets extracted from these. They have like these triplets, and they're looking for answers basically to these test questions, right? So it's quite a challenging task. And they have assembled a data set, which is, it's not huge, but like given the difficulty of assembling this, it's pretty big, of 4,000 trading questions-ish. So this is mostly intended to just give you a flavor of like the kinds of tasks that BioAsk has put out in the past, and that you could get, you could play with if you're so inclined. I'll also mention there's been a trend, I think, in NLP broadly towards these multi-corpus benchmarks, and the biomedical space has not been an exception to this. So a couple of years ago, or maybe it was, I guess 2020, Blurb came out. This is a biomedical language understanding and reasoning benchmark. It's a collection of tasks that include sort of classification and information extraction. Here I'm showing the set of tasks. You'll note that at the bottom, these are mostly probably, who knows, like, it's not clear what these task names mean, but you'll notice that BioAsk, which I just mentioned, is like sort of one of them. So it's like a bunch of tasks that people kind of put together, and you can kind of evaluate different, for example, Muppets against these things. And so that's kind of the idea behind Blurb. Another one that just came out is called Big Bio, and this is really focused on zero-shot stuff. So this is basically, let me see. So, right. So that image is rendering terribly, sorry, but it's a big collection of different tasks. I'm not sure what happened to this image, but it's a collection of different tasks where it spans quite a range in terms of what you're trying to do. And also it does include, I think, primarily biomedical literature, but it also includes data from electronic health records, which I'll talk about later. And, it's everything from like question answering, classification to some other tasks as well. So I hope all of my figures aren't like this, but here we're showing sort of zero-shot performance across different models on the rows here are models, and this is like an aggregate measure across tasks. And what this is showing is that there's a lot of room for improvement, I guess, basically. So I guess the only thing I would ask to take away from this is this big bio thing is out there. If you're interested in zero-shot learning specifically, you might check this out, especially in this space. All right, so that's kind of like a little bit of an overview of, I guess, different shared tasks that are out there, and how people are working with, or like how people are thinking about designing tasks and data sets for the biomedical literature in general. I want to talk a little bit more specifically about a particular area that I've done a lot of work in, which is basically retrieval and language technologies to support evidence-based medicine specifically. So if you're unfamiliar, evidence-based medicine is this idea that you should use explicit and judicious, you should explicitly and judiciously use the current best evidence to make decisions about caring for individual patients. This maybe doesn't sound like a radical proposition to you, but at one point was, I think, in medicine. And the way that sort of evidence-based medicine works, at least classically, is one is going to have a particular clinical question in mind. And typically, we formalize these questions in terms of what are called the PICO elements. So the PICO elements are the population, which includes like the condition, for example, COVID-19, or it could also include sort of demographics like women, right, or men, or what have you. So in this example, women with hypertension would be the population. The intervention and the comparator. So the intervention is typically what one would think of as like the active drug or the active treatment. So it might be like aspirin, or in this case, regular exercise can be the intervention. And usually your question is, in this population, does a particular intervention, say exercise, outperform some other intervention, no regular exercise, or maybe it's placebo, with respect to some outcome, and that's the O, right? In this case, hypertension. So typically, you think of questions in terms of pico frames, and you're looking to find all of the evidence that's relevant to that pico frame, to that clinical question, and you want to aggregate it somehow. And when I'm talking about evidence here, I'll be limiting myself to randomized control trials, which remain sort of the gold standard in terms of estimating the causal effects of interventions. Of course, other kinds of evidence exist, but I'm limiting. I'll sort of limit the focus here to RCTs because it's this is sort of the gold standard, and it's simpler to start with RCTs, I guess. Okay, so Individual trials, however, like if you just look up like like one trial on the effects of exercise on hypertension or whatever, they're noisy, right? So they tend to have, they may have small samples, they have their own biases. So in evidence-based medicine, the preference is to do systematic review or meta-analysis. And the idea here is you're going to find, like I said, all of the trials that have been done that are relevant to your PICO frame, all of the trials on, exercise for hypertension or whatever. And you're going to identify the relevant ones and extract from these the effect sizes and the sample sizes or whatever else you need. And you're going to put those together statistically. And you're also going to probably write like a narrative synthesis, right? That basically describes like, okay, on average, basically, exercise did have a positive effect on hypertension or whatever. So that's the idea behind kind of systematic review or meta-analysis, right? And so a good example of this, and one that's certainly near and dear, I guess, to my heart now, is drug treatments for COVID-19. So if you look on the BMJ, the British Medical Journal actually maintains like a living systematic review and what they call a network meta-analysis, which means they're looking at multiple kinds of interventions on different treatments that are available for COVID-19. And they're trying to keep this up to date as new evidence emerges. So, right, this, I have to update this screenshot, but anyway, they've kept us up to date. And I think they had something, this was outdated, but they had something like 72 trials spanning 40,000 participants, which I think is much, much bigger now. And every node here in this graph that I'm showing is like a drug, and the edge denotes that it was compared, that these two things were compared. And so this is very useful. Like it would be nice to have, basically you can, this compiles all of the evidence that's buried in these natural language articles and makes it kind of usable. You can immediately read off. If you know how to read this thing, you can know like sort of what treatments seem most beneficial, basically, for different outcomes, right? And like I alluded to, like the reason that this is an IR summer school, why am I telling you about network meta-analysis? Well, because like to get there, to keep that thing up to date is a huge amount of work, because you have to kind of keep up to date with, you sort of have to monitor sort of, I guess, all journals that might publish new relevant evidence pertaining to, I guess, COVID-19 treatments. And then even when you do find them, you have to extract from the publications, like the information that you need to update your living systematic review or your living meta-analysis, right? And so I think as language technology people, right, like the potential is there to try to sort of expedite that process. And that's the fundamental proposition here, right? And just to kind of, really submit that point, on average, it takes something like 67 weeks to complete and publish a review, right? So by the time it comes out, it's probably already out of date, probably new evidence has emerged. And the problem is getting worse, right? So if you look at just the number of randomized control trials that are being published, it's sort of already vast and growing very rapidly, right? So the most kind of fundamental like IR part of this has to do with what is sometimes called abstract screening. So in the standard workflow for systematic reviews, what you're going to do is issue a high recall Boolean query. And I should really emphasize that in this space for like meta-analysis, the emphasis is almost always on recall or sensitivity, because it's important not to miss any relevant evidence. So what you'll often see people do is they'll write these like sort of high recall Boolean queries on, say, PubMed, like I was showing before, and then retrieve a big set, maybe order 5, 10, 20,000 potentially relevant articles that are maybe relevant to your PICO question. And then you're going to screen those. You're going to read them, and you're going to say, this is relevant, this is not relevant. And you'll set aside, you'll sort of screen in the set that's actually relevant. And often this may be, 5, 10% of the things that you retrieved with your initial Boolean query. So this is like sort of how the typical workflow goes. And so like one thing we can try to do is semi-automate that process by treating this as a learning problem, right? So you basically, you start with this sort of unlabeled set, which is the set that's retrieved from PubMed, and you do some sort of learning process, either kind of standard supervised learning to rank or learning to really discriminate, or you can do some active learning stuff. And ultimately what you want to do is help find the relevant things within the pool that was retrieved with that query more efficiently than would happen if they just kind of went through the whole thing in the typical process. So a long time ago now, I sort of did a bunch of work on this. Other people have obviously worked on this as well. But I guess what I would say about these technologies, if you take that view of starting with the set of articles retrieved from PubMed and then building technologies like active learning strategies or other methods to semi-automate the process from that as a starting point, this is pretty successful. You could certainly expedite the process somewhat, and there's actually been so we've released like an open source tool a long time ago called Abstractor that facilitates this, that makes these, like, allows you to basically do this, like upload your set of articles and start screening, and it will do machine learning in the background and try to exclude irrelevant things from what you've uploaded based on your labels. And there's been a bunch of other tools that have come out since then. And there's been actually a bunch of like independently published sort of evaluations of these technologies and like, do they actually reduce workload? And they do. It can be, it varies, but you can certainly get savings. So this is cool. Like, this is an example of a case where just deploying this kind of technology really does help people to produce systematic reviews faster than they otherwise would be able to. And so I think it's a nice kind of win in that sense. Right. And so I think this latest trial that was published in May of this year actually found that you reduced the workload by 67% compared to, I guess, the typical approach. And it did so without omitting relevant citations, was their conclusion. So, it's sort of nice to see this kind of analysis. However, like, that strategy of like, okay, let's just start, let's sort of operate within the paradigm that the systematic review people like, which is start with that Boolean query, the very high recall Boolean query, then sort of machine learn your way to optimize the process from there. Like, that's okay, but there's some more recent work that I think is cool. A lot of it done by Harris and Scales, which is sort of looking to do the thing end to end. So it says, forget the Boolean query to begin with. Let's just do like end to end sort of query formulation and basically try and think about the process as interacting with the entire set of the literature instead of sort of starting with that like initial set that's retrieved with a simple Boolean query. So if you're interested in this, like I'd point to that work that's much more recent than the stuff that I mentioned earlier as well. And there's like a whole line of papers along these lines that I think is pretty cool. More recently, we've been thinking about, and this is work that I've been doing with my collaborator, Ian Marshall, who's a real doctor. We've been working on sort of like beyond sort of just sort of classifying these things as being relevant or not to a given Pico question. You sort of want to extract the actual underlying elements that would then support richer querying, I guess, right? So you want to basically extract, for example, what are the Pico elements from this article and other similar things so that you could then do more interesting things when you sort of query that data. So to this end, we've been developing this thing that we call Robot Reviewer. And this is like a suite of models that consumes articles describing randomized control trials and produces structured information from those. So it's probably easiest to see like a little demo here. So basically the idea is these are a set of PDFs all describing randomized control trials, and you sort of upload them and it does its thing in the background. Disclaimer, this was sped up. And then it produces like a bunch of structured outputs. So it'll try to like assess the risks of statistical bias in the respective studies. For each study, it tries to extract sentences describing the populations, interventions, and outcomes. And you can kind of click through to the PDF to see like from where these were extracted. So, so this is something that's kind of intended to help people, I guess, navigate the literature faster is the intention here. And we've been kind of working on extending this sense. So one thing that's nice is like actually that BMJ article that I mentioned, they actually are using one of the robot reviewer models to identify the randomized control trials. So we have one of the models in robot reviewer says tries to say automatically whether or not a given article is a randomized control trial, which is surprisingly does not exist. Like there's no other way. There's no like sort of there was no way prior to that of just asking for like all RCTs, all randomized control trials. So we thought that was cool. So more recently, and I think relevant maybe to this this summer school in particular, like we've been trying to index. This kind of gets at what I was saying before. Like there's actually no good single place to get all randomized control trials, which is like a lot of times that's what you're after. So we've been trying to create such a resource. And so what we do is we monitor PubMed as well as some other sources like clinical trial registries every day. And we run newly indexed articles, many of which will not be reports of randomized control trials. We run them through that model I mentioned in Robot Reviewer, and we classify each as being a randomized control trial or not. And the things that are randomized control trials, we pull in, and we run those things through the suite of models that's in Robot Reviewer. And this does things like it extracts the sample sizes, the pico elements, which are text snippets. It tries to assess risk of bias, which I haven't really explained, but is basically a proxy for the reliability. And also like the main findings, and it dumps these into a structured database that we call Trial Streamer. And right, so I guess this is the whole kind of pipeline. Again, a little bit redundant with the prior figure, but basically, yeah, we do article retrieval, then we do a suite of extraction modules, basically. So Trial Streamer then is like a database of semi-structured information for all RCTs that are out there, that are published, basically. So you can use this to, so this is what the prototype looks like. We make the database, like the underlying data available itself. You can download that as a Postgres database. And then you could also use our little prototype interface here to search. And one thing that we do is we allow for like faceted search because we extract the populations, interventions, and outcomes from each article. When you do a search in Trial Streamer, the idea is you do a search such that you search for a specific population. For example, COVID-19 might be your population specifically, and a specific intervention. So for example, remdesivir might be the intervention that you're interested in. And then we do a pretty basic match based on, we normalize the snippets that we extract from the articles to mesh terms. Those are terms from that ontology I mentioned. And we just basically match the query that's entered on those mesh terms. So that allows for normalization for different sort of spellings and so forth. So that's basically it. And what Trial Streamer will do is it will surface for you. Here I'm showing the result of this COVID-19 and remdesivir search. And it surfaces the relevant trials in order of either the most recent or the sort of largest, because often you want large trials. And we show what we sometimes call the punchline, like sort of like the main finding, which we automatically extract, as well as like the sample size and the snippets that correspond to those pico elements that we automatically extract. Right. So also the risk of bias as best we can estimate. So that's the idea there. If you're interested in this kind of thing, like one of the things that we do, aside from making the database available and updated, which we update, I think, daily, we've also tried to make the models themselves like easy to use. So we have a version that you can pip install, and it's all sort of based right now. Like we have in this version, everything is based on top of Cybert, which is a version of BERT that was trained on scientific literature. And so it will download those weights like as needed. So if you're interested in this kind of thing, you could check this out, and it will sort of give you back structured output if you give it a title and abstract of a randomized control trial that looks like this. So it tries to tell you, okay, here's what I think the main punchline, the main kind of takeaway text is. Here's what I think the direction of that finding is. Here's whether I think this is actually in an RCT, and a bunch of other stuff as well. So I'd point you to that if you're interested. So we've been kind of moving towards, this is a little bit more experimental, but like the dream would be to skip the middle step and just go straight to the narrative review, right? So you just enter a search. So enter like your population and maybe an intervention, and you just want like a narrative to be produced for you that synthesizes all of the evidence out there pertaining to that that population and that intervention. So here's actually what we've been looking at this. So this is basically just like summarization, and you can do this. So this is the actual this is a real output that we integrated with TrialStreamer. Where what we do is we just take like the top 10 trials retrieved for a given query, and we stick them through a neural summarizer. In this case, it's BART, and out comes like the summary that's basically talking about whether or not there's evidence to support the use of hydroxychloroquine, I guess. Right now, you do get text that looks like pretty plausible and is certainly relevant. But there are some caveats here, of course. So let me just talk a little bit about what we're actually doing here. So we're not doing anything too fancy. We just take titles and abstracts of inputs. These are like individual articles describing randomized control trials that address the topic of interest. We just kind of put special tokens between them and then shove them through an encoder-decoder architecture. So in this case, we are using BART, which is a particular realization of this. And this thing is trained in such a way where basically the encoder looks like BERT and the decoder is autoregressive. So it generates one word at a time, each conditioned on the last. And that makes it amenable to conditional generation tasks like summarization. And so we trained this thing using previously conducted systematic reviews for which we know what the inputs were. We know what the titles and abstracts of the corresponding randomized control trials were. And we have human written summaries, expert written summaries of the evidence. So we have a data set of like 5,000 or so of those, which is publicly available. So we can train this thing up, and it does okay, like when you just kind of look at it. Like in terms of Rouge, never mind, this is like a bunch of different models that I won't describe, but that's what's on the x-axis. But I think the point is that like they all look the same in terms of Rouge, basically. And I think the key takeaway here is that Rouge is not meaningful at all in this case, or maybe any case, I don't know. But like what we did was we actually had people assess, we had medical doctors assess like the relevance, or sorry, the factuality of the generated summaries. So we asked them basically like, we showed them the system generated summary, then the human written summary for the same inputs. And we're like, do these align factually? And the answer, these are human written statements. And if you look at the bottom row, which is factuality, the answer is no. Basically like the summaries that these systems produced are like relevant and fluent, but not factual. So this is very bad. Here's an actual example. So like the system will, if you ask it about COVID-19 vaccines, it's like, yeah, vaccines cannot be recommended for routine clinical practice. We need more RCTs, right? And so the model maybe not so good. So I think there's a lot of challenges in terms of doing sort of these, I guess, QA style generation exercises. Like we're just kind of not there yet. And the reason we're not there now is because like we don't know how to ensure that the output will reflect the evidence as it's actually reported. So that's most of what I'm going to say for biomedical literature. I guess one thing I'd like to emphasize here, like especially if you're just kind of getting exposed to this general space, is I do think it's an area that has potential to have like sort of real impact for social good. And I do think there's a lot of like easy wins where there are a lot of problems that like existing technologies can do a lot of good. So a really concrete example of this is I mentioned that we built this like RCT classifier. We didn't do anything really that interesting from the methodological perspective at all, but it actually turned out to be pretty useful. I think like people really do use it. And it met a need. And so like, if you find that kind of thing satisfying, it's a very good area to get into. And it also does motivate. It's not always so easy. And so there are like technical challenges, which usually boil down to not having very much supervision, in stark contrast to sort of a lot of other areas, right? It's very difficult to acquire expensive annotations from physicians and what have you. There's lots of readily accessible data and tasks, like I mentioned, and there's lots of challenges. And I think, again, like first and foremost, I think really understanding what is actually going to be useful is like maybe the hardest problem. And so what my advice would be is if you do get into the space, or really whatever space you get into, you really want to, if you're going to work sort of, especially on the more applied side, like you really want to work with domain experts to understand sort of like what they actually want built and sort of how the technologies that you would build would sort of interact with their domain expertise. All right, so that's all I'm going to say about biomedical literature. I'm going to shift gears and talk a little bit about social media. If anyone, we can do questions as we go. I should have specified that up front. I'd be happy to take them, or I can just kind of dive into social media. I can kind of see hands. I don't know how this would work, but if anyone wants to interrupt. But otherwise, I can talk about sort of some social media stuff next. All right, I don't hear any interruptions, but you're free to interrupt whenever. So at a broad level, social media there's a pretty long history of, well, by CS standards, of using sort of social media as pertains to health, right? So a lot of this has to do with like sort of surveillance in the sense of, not in the like nefarious sense, but like just kind of like monitoring for like epidemiological reasons. So, like looking at like flu prevalence or what have you, right? So I think Google Flu Trends was like a really early example of people trying to do this, where they were looking at basically like queries, I guess, for like flu-like symptoms, more or less, and then correlating this with CDC data about like flu levels. And that said, there were like, there were some issues that came out with Google Flu Trends later. I don't remember the details here. It was actually my colleague, David Lazar, made some good points about like sort of problems with this approach, I guess. But nonetheless, I think there is some potential for sort of monitoring, I guess, search trends for like epi type stuff. Another interesting example of this was some work by Michael Paul and Mark Dredzy, looking at, this was some early work looking at like sort of Twitter for, I think, this was also for flu. And sort of, you can sort of do similar things where you can like sort of harvest social media data to kind of monitor like what's going on at a population level with a given disease. Another kind of cool example, also by Michael Paul, another cool kind of unique example of looking at like sort of search trends was this work on looking at sort of the history of an individual kind of illness trajectories. So they looked at like search trajectories. I think this was for breast cancer. And I guess what you see is toward the beginning, people are like searching more for symptoms, as you would expect. And then they get like a diagnosis, and eventually they're looking for like treatments and so forth. So this is kind of interesting, almost qualitative work looking at what search histories say about the trajectory of disease. Okay, so this is like the survey portion. The other thing I would point you to, there's a lot of work, as you might expect, on sort of looking at social media and what's posted on it as relates to COVID, right? So if you're interested in that kind of thing, like I'd point you to there, I was sort of involved. So I guess the disclaimer here is I was sort of involved in organizing these, but there were these 2 workshops on NLP for COVID-19 at ACL and then EMNLP in 2020. And there's like a bunch of work there if you go through the proceedings on sort of social media related content, especially. And so one example of this is this COVID lies data set where they're trying to like sort of detect COVID-19 misinformation on social media. And I think that includes a data set, I believe. So if you're interested in that kind of thing, you might check that out. Here's an example from that data set. So I think the idea is that they align tweets with sort of misconceptions that were held in the greater population, I guess, and they labeled tweets as like agreeing with said misconception or disagreeing with it or taking no stance on it, right? Okay, so I'll talk now in a little bit more detail about this work that we've recently done looking at health claims on Reddit. So the idea here is that Reddit is really like, there's these subreddits on Reddit, if you're not familiar. These are sort of like communities dedicated to particular topics. And so what you'll find is that for a lot of, especially for like chronic conditions, you'll find very in-depth discussion by a lot of people on different health topics. And so we set out to annotate a set of these, and we're really focusing on claims here, but we also annotate other kinds of experiences as well. So here's the kinds of annotations that we did. We've got like a Reddit post, and the one thing that we do is we tag the Reddit post with Pico elements, right? Which I mentioned earlier, of course. So these are the populations, interventions, and outcomes. And the other thing that we do is we tag spans. I think we operationalize this as sentences as containing a claim, like, you know, X cured my Y or whatever, as well as questions and personal experiences. So these are like the categories that we separated out. And right, so that's kind of the annotation scheme that we came up with. We picked like a bunch of subreddits corresponding to a diverse range of conditions. These ranged from very common conditions to very rare conditions. And we collected thousands of annotations for each subreddit, for each disease community, basically. So what we were interested in doing, and what I'll talk about here specifically, although you could do other things with this data set, we wanted to look at whether or not we could try to retrieve evidence that was actually trustworthy, relevant to a given claim made on social media. So, right, so the idea is that somebody comes along and they say like, hey, bleach cures COVID or something, and then you want to be able to retrieve, you want to be able to say like, is there any evidence that's published that actually supports this claim, right? Or maybe contradicts this claim. So to operationalize that concept, and for more context, like I think what I had in mind here is sort of like maybe this would permit moderation. Maybe this would help moderation, right? So if you're a moderator of a community, you don't want misinformation. And so there may be cases where like it would be nice to be able to contextualize claims that are made by people, which will not always be so egregiously wrong as the bleach example. You might want to contextualize these claims with access to trustworthy evidence. So that's the idea. So to do this, we want to be able to extract, we want to be able to, first of all, recognize when a claim is being made. And then we want to extract Pico elements from the claim. And then we want to retrieve published evidence. Namely, we want to look at RCTs because these are the reliable things that match up with those Pico elements that we extracted, right? So that's the idea. And so, right, so just as a concrete example, if somebody comes along and they say, hey, you know, vitamin D might prevent autoimmune disease, like, is this true? I don't know. So if we go out to Trial Streamer and we say, like, are there any trials that actually support this claim? It turns out I think in this case, there is maybe. I'm not a real doctor, but right. So like, it's nice you can actually find relevant articles that might contextualize that claim and might help either the moderator or people reading this on social media to come to their own kind of conclusions as to the veracity of said claim, right? So that's the idea. And I think the key thing from the retrieval perspective is like the recognizing that vitamin D is the intervention in play here, and autoimmune disease is the outcome in play is really kind of critical in doing this retrieval step accurately. All right, so how are we going to do this? So what we do is we take as our representation of the claim. So I'll index the claim by J. We're going to take the whole post that contained the claim. I'll call that P. And we're just going to concatenate that with the claim span, which is like within that post. And also the population span that we extract, the intervention span, and the outcome span. And we just concatenate these things with special separating tokens, as you might expect. And then what we're going to do is we're going to just use like a dot product similarity where the dot products are between encodings that are yielded from two separate encoders. So we've got a claim encoder and we've gotten like an abstract encoder. And the abstract encoder is responsible for consuming an abstract that describes a randomized control trial, right? And it gives you back the vector. Okay. So of course the encoders are just sort of your favorite Muppet, I guess. But this is the similarity that we're going to use. And we're not going to do anything too fancy. Like so you could just kind of do that in a roughly unsupervised way, and we'll see the performance of doing so in a bit. But ideally we would sort of learn to rank evidence in terms of its relevance to particular given claims, right? And so you can imagine doing this by fine-tuning your encoders to optimize an objective that says to basically push a claim close to relevant evidence in this space, as measured by the dot product, and that's relative to its distance, I guess, to irrelevant abstracts, right? And what we do operationally is we sort of normalize this term using like in batch irrelevant abstracts. So basically you assemble a bunch of abstracts together that you're going to put together in a batch. And the idea is that the relevant abstract is accompanied by a sort of a set of B irrelevant abstracts. And that's what we're going to use in the denominator here. So the problem is, like, to optimize this objective, we need supervision, but we don't have it. So supervision here would look like claim and evidence, right? So you need to know, like, okay, here's a social media claim, and here's a piece of evidence, an abstract that's relevant to it. So we don't have it. So what we do, and this is like a little bit of a theme here, as I mentioned earlier, like supervision is a constant problem in this space. What we're going to do is we're going to use sort of a heuristic or distant supervision strategy. So we're going to start by pairing an annotated claim from Reddit, right? So you have some social media post that's like making some claim. We're going to pair that with an article in Trial Streamer. And in Trial Streamer, we know, because we've automatically extracted the populations, interventions, and outcomes. So what we do is we take the spans that have been annotated as containing the same elements, the Pico elements, and we just like substitute the elements in from Trial Streamer, right? So you have the Pico elements from a particular RCT, and you just drop those into the post on Reddit in the locations that correspond to the Pico elements. And you treat this as a positive example, right? Because now you have like a you have your claim, which is like the social media post, and you've got the target, which is like an RCT that has those same fecal elements, right? So here maybe it's easier with a concrete example. So here we've got somebody saying, oh, I'm surprised that I'm seeing research articles that some intervention causes an outcome. So originally, of course, those had an actual intervention and an actual outcome. We kind of replaced them here. We like templatize this here, and we just pick an article from Trial Streamer, and we drop in a particular drug and a particular outcome. And the article from which those came from becomes the positive example, right? So the idea is that like this allows the model, we hope, to sort of learn to map, I guess, from like the sort of natural language that's used in on Reddit, for example, with it sort of learns to match that to the more formal kind of language that's used in these scientific articles, these articles describing RCTs. And okay, so does this work? So compared to sort of like a pre-trained this pre-trained DPR model, which is short for deep passage retrieval, I think. This was the strongest baseline that we evaluated in like sort of preliminary experiments, and then we went and we had doctors assess the relevance of retrieved articles to given claims, and so what we find is that this model that we trained with the pseudo data that I just described, it ends up yielding more relevant articles at K for K for K1 through 10 than the strongest comparable kind of baseline for doing this retrieval. So I guess like maybe the takeaway here is like if you're able to design kind of like these distance supervision strategies, then you might get some wins from fine-tuning your encoders in a setup where you're doing sort of I don't know, deep passage retrieval like exercises like this. So so that's the idea there. All right, the last sort of area that I wanted to talk. Well, let me pause again. Does anyone want to interrupt with any? Offer a welcome interruption with any questions, or I can continue on to electronic health records.
Any questions? Okay, but I think you can continue.
All right. So the last sort of modality that I'll talk about is electronic health records. So electronic health records, they've been around for a long time now. There was a nice New Yorker article a couple of years ago that was talking about why doctors hate them. And I think that these reasons is sort of why I think sort of IR, for example, has the potential to make electronic health records less painful, right? So so just broadly speaking, electronic health records are stores of sort of patient information, and I guess obviously the history that the patient has had. And I guess the thing to reiterate here is that a lot of the data in electronic health records are unstructured. So there's a lot of notes that exist within electronic health records, and that is maybe more difficult to make use of than would be ideal. Right. So there's been, as you might expect, there's been a fair amount of work on IR in medical records. So some possible or sort of example tasks include retrieving snippets from notes within a given patient's record that are relevant to a given query or image. Right. So there's been a lot of work on that kind of thing. Another area, or sort of, and I'll talk more about that in a moment. Another kind of topic that there's been a fair amount of work on is retrieving patients eligible for given clinical studies. So these are just two examples, but there's a bunch of stuff that you might imagine doing that would help make better use of electronic health records. I'll just highlight that there were some TREC tasks. I don't think they've done any recently that were specifically relevant to EHR, but I'm not totally confident in that. But there were some older interesting TREC tasks that were specific to this latter bullet point, where the task was to match patients eligible that looked eligible for clinical studies based on their electronic health records. So you might check that out. Okay, so I'm gonna sort of talk about some work that we did in the space, which was trying to build models that could provide extractive and query-focused summaries, which are really just sort of collections of extracted sentences, basically, of electronic health records with the intent of aiding diagnosis, right? And so this is a particular work in this kind of broader, I guess, subfield, I'm not sure, of looking at trying methods for summarizing in some way the electronic health records data for a given patient. If you're interested in this more generally, there is a nice survey, slightly dated, from Nomia El-Haddad, that covers like sort of other work in this space, but I won't talk about that work. Okay. All right, so the motivation here is as follows. We work with a radiologist. This is Jeffrey Young. He's at Brigham and Women's Hospital. And basically, he feels like there's often information in electronic health records data that would help him when he's diagnosing imaging, right? So he's looking at imaging like brain scans or something. And he thinks that there's probably notes in the electronic health records that would basically inform his diagnosis, but he doesn't have time to wade through the record to find them, right? So what we'd like to do, and this is work led by Jared, who's shown here, we'd like to train a model to provide extractive summaries that are relevant to a given query or a potential, which we'll kind of view as a potential diagnosis. So, right, so the doctor might think, okay, like I think this is what the case is, like I think this is a stroke or something, and what we'd like to do is extract from the medical record snippets of text that might support that diagnosis. Right, so that's the idea. Here's kind of a schematic of what this would look like. There's sort of a history within this patient's CHR. They present on some particular date with like a headache, and the doctor is looking at the MRI and queries, oh, is this like maybe this is a stroke? And the idea would then be to compile a summary that provides evidence that would be relevant to that diagnosis. So I think this is a medication that if you stop taking might lead to stroke or something in this particular case. So that's kind of like what we're trying to do, right? Because he doesn't otherwise have time to go through the record to find this information. All right, so formally, what are we going to do here? We're going to sort of have a we're going to sort of model this as we're going to have X, which is like sort of the patient electronic health record, segmented in some way. I think we'll do sentence level segmentation here. So we'll just assume that we have like sort of a sequence. We have like a sequence of sentences, let's say, associated with this patient, which we'll call X. We've got a query, which I was saying was like stroke before or something like that, but it's any natural language query. And then we want relevance scores, which would be the same dimension as X, basically. And it would say like sort of how relevant each sentence or whatever unit you're using in X is to the query. That's kind of what we're trying to do here. So one thing that you could do is sort of an unsupervised approach, right? So you could basically just encode your query, which here is called Z. You could just encode this thing into so that's just the notation for taking sort of a mean representation over a transformer output. So you're going to shove both the query, so that's DQ, and the sentence in a particular sentence within a patient record, X sub I. You're going to shove them both through a transformer and then take like a mean or some other pooling mechanism to get a fixed length representation of each. And then you could just, take the dot product or cosine similarity or whatever, and that can be your similarity score, right? So, so this is kind of like the simplest thing you could do. And I should mention here that there are versions of, there are like clinical BERTs and what have you, right? So you can use as your transformer, a clinical BERT or whatever sort of Muppet you'd like, right? So that's kind of the simplest approach. I mentioned that this would be a little bit of a theme, and I meant it. So like I think again we would prefer to be able to sort of do some learning, but to facilitate this we need supervision, and again we don't really have it. So what we did in lieu of supervision is we had radiologists on our team. So Dr. Young and his colleagues, they enumerated a set of ICD codes. So ICD is International Classification of Disease Codes. And these are contained within the medical records. And basically, we had them enumerate a set of these that correspond to diagnoses of interest, like stuff that they think is like sort of that they find themselves diagnosing often as radiologists. And then we get labels for free, right? Like we know which patients are associated with which of these ICD codes because ICD codes are attached to their medical records. So what we do is we train a model to predict future occurrences of these codes. So we don't actually care about this task. Like we're not trying to anticipate the onset of these particular ICD codes as such, but we're interested in doing this as a proxy task. Like we're interested in doing this to ultimately provide relevance scores for individual sentences to queries. So when I say future occurrences, I mean like you have patient records. So like if you look at let's say just the notes from time 1 to time t, then you can say, I know at time t+1 that record was associated with this ICD code, this outcome. So I'm going to predict that from the records 1 through t, right? And so so that's what we're doing here basically. And what does this look like? Well, we take the report, we take the sort of X, the let's say the sentences ordered sequentially associated with a particular patient. Here, each sentence is demarcated by a different color. And we run each of these sentences separately through a clinical BERT. And then we also run the query through a clinical BERT. And we can take then the sort of the product or some other measure of similarity between these things, and we get a ranking over the sentences with respect to that relevancy scores, right? And this query can either be just like a natural language query, but in this case, remember that we're using distance supervision. So the query here is the corresponding ICD code, right? And this is actually drawn from a hierarchy of codes, and we'll actually try to exploit that fact, right? Oh, sorry. And the final prediction is 0-1, which is basically like, does the patient have develop this ICD code? Like, does a note at time t+1 or beyond have this ICD code? So it's a predictive task for ICD codes. And so in terms of scoring, we're using basically the same function as before. It's really always the same function. So we're basically just taking, in this case, we use the CLS token from the transformer for the sentence X sub I that's associated with this patient, dotted with the embedding of the query that we get from the transformer, E sub Q. And then basically, we just want that to be comparatively large, right? And so we make a prediction. This is an unnecessarily notation-heavy realization of this, but basically we just make a binary prediction. This is the proxy task that I mentioned, where we're trying to predict, does this patient actually have this code in a later record? And when I say this code, it's Q. It's like stroke, or the ICD code associated with stroke. And for this, we just use a multi-layer network that's using the same representations that I just mentioned. And so we I guess the only thing is that we use the similarities between the query and the sentence xi as a means of informing the weight for the individual sentences, right? So again, we're learning these sort of soft weights for each query, and sentence to predict a binary label as to whether or not the patient in later records exhibits or features an ICD code associated, the ICD code in question, right? So the whole idea here is basically to treat ICD codes as queries and then make binary predictions pertaining to these. And in this way, you get a soft weighting over sentences. So how do we embed these queries? Like, you do have a couple of options here. You could just do like one hot embedding of queries. That would be like into ICD space. ICD codes are also associated with descriptions, though, which is preferable because at test time, we want people to actually be able to enter natural language descriptions, right? So that's kind of like, that's sort of the baseline mode in my view, is you just like pass the natural language description to BERT or whatever. But I mentioned these are also drawn from a hierarchy. So one thing that we tried doing was you can take a path through the ICD hierarchy to a particular node within it, and you can concatenate the descriptions for all of the codes along that path into like a big natural language query. So that's like you're like expanding the query, I guess, and you're giving like the full path. So we also tried that. So we actually had, what we did was we allowed radiologists to evaluate this. We did this in a couple of ways. We had them kind of annotate. It's a little bit complicated because we had them like look at, we had to pick a time point and then say like, okay, now look at future reports and like figure out like what queries might have been useful for you, basically. But ultimately, they're going to give us manual judgments that say whether or not they think that the system is able to retrieve from the historical patient information sentences relevant to queries that they provided. And they were just able to pick what queries they entered, basically. And so what this plot shows is that a bunch of different kind of methods, hopefully many of them would be like sort of very basic things like TF-IDF and cosine similarity being between the unsupervised outputs of, I think, clinical BERT in this case. And then basically using the description and hierarchy encodings of the query and distance supervision to fine-tune the model with the proxy task of predicting future ICD codes. That actually does yield considerable boosts in your AUROC and also, I guess, your precision sensitivity curve, your AURPRC. So you do get gains. So again, like, I guess maybe the take home here is when you can, like, exploiting sort of noisy supervision as best you can come up with it is often beneficial. I guess this is the second time I'll make that point. And again, I think like in medical domains in particular, this is important because like pain, like even, I forget how many we collected here, I should know that, but it's in the paper, of course, but even doing this just for the evaluation, collecting the actual relevance judgments, and we're talking order hundreds here, very expensive because you have to sort of pay radiologists to do this and they're already pressed for time, right? So it's very difficult to get supervision at scale if in these spaces. Okay, so that's most of what I wanted to say. I know this was like a little bit of a whirlwind. I hope it was in keeping with I don't know, the spirit. Like my hope was to provide sort of like a set of illustrative, I guess, pieces of work in this pretty broad space. I guess what I would say is I think IR and I guess language technologies more generally. Again, really, there's a lot of room for realizing impact in this space. There are lots of resources to get started. Like I said a couple of times, like supervision at scale, very hard. That's probably one of the main challenges. One of the other main challenges that I actually didn't talk about too much, although I do work on it a lot, is varieties of interpretability, right? Is like pretty important in the space, depending on what you're doing. So that's kind of like a whole nother aspect here. And I guess I would close by reemphasizing that I think it's really critical to work with domain experts when you're framing these problems instead of just kind of like building something because you can, I guess. You know what I mean? Like, I think if you want to have impact, the best way to do that is to make sure you're solving a problem or working on a problem that somebody actually cares about. So I think if you're going to work in the space, like try to find collaborators that know the space, I guess. So that's it. Happy that we have time for questions. And again, I'm sorry I had to be remote from very close. But I'm happy to take any questions. And thanks for the time.
Okay, thanks, Byron. So, questions then?
Yes. What do you think of using the last model that you showed to inform patients before they develop the disease?
Sorry, could you repeat that one more time?
The question concerned the application of the last model that you showed, how important it can be in order to inform and try to tell patients about potential problems that may appear later. Right.
Oh, that's interesting. Yeah. So, right. So, I don't know that I would give it to patients because we are using. It's interesting. So we're predicting the onset of conditions as a proxy task. There is plenty of work of people predicting these, for the sake of predicting them. I don't know what you would do with that. Like, if you just told a patient, you might be at risk of developing this condition, I'm a little bit skeptical about that being particularly useful. However, we have thought about using these proxy models in a different way, which is that I mentioned that what we've proposed doing so far is basically retrieving from the patient records snippets that seem to support an initial diagnosis that a radiologist suspects, but this might actually just be kind of a confirmation bias thing, right? It might they have some initial suspicion, and then you give them evidence that supports that, and it's okay, that's definitely it. We've actually thought about using the model that predicts the ICD codes to provide, when the radiologist gives you an initial diagnosis, here's what I'm thinking, basically, you could give them back the evidence that supports that diagnosis, but also other plausible diagnoses that are predicted by your model and evidence from the record that supports those other plausible diagnoses. And the hope is that might counterbalance this kind of known phenomenon of confirmation bias. So we haven't done it yet, but it's something that's kind of how we've been thinking about using the actual kind of proxy task model. But yeah, it's a good question. I don't know. You might be right. Maybe telling people you're at risk for this, but I think it's very difficult to interpret these things, and also the predictive capabilities in terms of being able to predict these things, it will vary so much with the particular ICD code you're talking about. So I don't know. I think you'd really want to think about it on a case-by-case basis, probably.
Hi, thanks for the presentation. You were nice talk. I have a question about the citation screening. So you were showing two approaches, the classification and the query re-ranking formulation. Sorry. And what would be the advantage or the disadvantages of the query formulation approach if it can be done unsupervised in contrary to having the labeled data set, right?
Yeah, I think it's a great question. I think in some ways the primary disadvantage would be, and this kind of gets at what I've been saying, it's almost like an acceptability thing. One of the reasons that when I was working on the problem that we sort of really took let's start with the initially retrieved set, is because it kind of fit in with what the systematic review people were doing and maybe would accept, whereas if you're telling them I actually agree philosophically with let's do away with that and do the whole thing in some sort of interactive search way. I think that's probably the right way conceptually. I think it's going to be hard to get buy-in from, there's a whole community that do this, right? The sort of, research synthesis community. And I think it's very difficult to get them maybe to wholeheartedly kind of buy into this radically new way of doing things, which is not a bad thing for research, but it does mean that I think that approach might, it's limited in that sense, right? So I guess that might be the one very practical downside, which again is sort of a strange downside to raise because it's not technical in nature. It's a sort of a societal thing. But yeah, I don't know too much about like my sense with I think the counterpoint is that the query generation stuff, I think the way that works, I wouldn't even call it unsupervised in this case. I think what that work was doing was like, sort of like you could view it as interactively building that initial Boolean query. And so that I think, and arguably so treating the whole pool of evidence out there as like the set that you're interacting with, that's the radical part. Then the not radical part is, and if at the end of the day, if I get a query that looks like what I'm used to seeing, right, then I can read that, right? Like if I'm like a medical librarian or whatever, can read that and know like, okay, well, this makes sense. So I guess you do get that kind of transparency. So I guess that's a pro. So I don't know. I guess it depends. I don't know that they've been compared head to head either. So that would be another interesting question. So sorry, I don't know that I have a super firm answer. Like I think the big question is going to be, what will people use? And I think the jury is maybe still out on the query formulation stuff, but I hope it gets used. Does that make sense?
Yeah. And do you think that the classification, like there is still like room for improvement for the classification, or like because there hasn't been too much like model wise, right? Like
yeah, it's all very depressing now because it's just like you shove it through BERT and like it does pretty good. I maybe like with some zero shot stuff could be interesting, maybe, but I mean the performance is pretty good. I think there are limits to what you can do because people want 100% recall more or less. They want, even though humans don't get 100% recall, like they think they do. So you want like 95 plus, let's say, with reference to human. So it's very difficult to push. It's very difficult to make any more gains in terms of precision under that constraint, I guess. So I don't know. Like I guess what I would say is, maybe it looks a little bit more like treat the whole data set, treat the whole world as the pool. Like doing some zero shot stuff maybe is of interest. Like I don't think there's been really any work on that. So like could you map like directly from like the query to the relevant set or something like that? I'm not sure, like some sort of hybrid where you're mixing the query with the learning of the discriminator maybe, but I don't know. So yes, there's still room for improvement, but it's very hard in that setting.
Okay, so other questions?
Yeah, and one question. Thank you, Brian, for your excellent talk. I just wanted to have your opinion about the summarization. So it's a great work to produce those systematic reviews and then produce a summarization. But then you end with one narrative about a drug or something. And it goes against sometimes with personalized medicine. So peanuts is good for someone, but peanuts can be the death of another guy. So what is your opinion on how to deal with that? Because we are living beings, we are very complex and a lot of variables. And in that sense, your PICO elements always is the details that you get from those PICO elements. Because, for instance, if I want a drug not to work on a clinical trial, I just give the wrong dosage, or I just give before lunch or after lunch, and it doesn't work. All these details are very important. That's one of the reasons why the Cochrane systematic reviews, they tend to use manual review because they have to have all these details on their model. What is your opinion about it?
So I think there are two separate questions there, right? Like I think Cochrane. So I guess there's the broader question about, which is sort of, I think, been kind of floating in the background for a while for sort of evidence-based medicine as such, which is like, how does this square with this personalized medicine stuff, right? Like, because basically anytime you're drawing a conclusion about populations, right, and the efficacy of treatments for populations, and like in some way that kind of goes against personalized medicine, right? Like it, but I guess personally, I'm a little bit skeptical about the whole, like my feeling on the whole personalized medicine thing is sort of that like we don't even do like evidence-based care at the population level, right? And so like what hope do we have for, I mean, you know, so I guess I'm a little bit skeptical about a lot of this stuff, but maybe I'm like old school in this sense. As for the subtleties, I think you're exactly right. Like I don't think that the automatic summarization, to me, this is more of like on the experimental side very much. Like one of the reasons I like it as a direction is I think it highlights very nicely some of the major problems, some of the major challenges in conditional text generation and summarization specifically, for the reasons that you, I think, alluded to. And this is why, like, you need, like, you know, Cochrane people or whatever to read through. Like, it requires, like, sort of doing a careful appraisal of the evidence that's reported, and then sort of like putting it together mindfully. And that's very, very complex. And you're asking a lot if you're just like shoving stuff through this neural network and you're just like, I hope that you give me all the subtleties and stuff like that. And what we see is it doesn't. And so it's nice to, it's sort of nice to work on a task where these models that seem to work, and maybe it would, maybe if you fed it like, you know, maybe scale would solve it, right? Because scale seems to solve so many things, but I don't think we'll ever have scale here in the sense that you have it in other things, right? Like we're never gonna have millions and millions of systematic reviews to feed into this thing. So, so I guess like in some ways it's an important problem, and it's one that I think readily surfaces many of the shortcomings inherent to the way that we currently do conditional text generation. So, you know, it's a good set of problems. Whether we'll be able to address them, I'm not sure. But I guess that's what keeps us in a job, right? But yeah, so those are my. And I don't want to, just to be clear, I don't want to be too hard on personalized medicine. There's a lot of good there for sure, and I think we can harness, like, combining population level stuff like RCTs with electronic health records data in useful ways. I think is probably a very cool direction that there hasn't been too much work in. So I, like, just to be clear, I'm not like anti personalized medicine. I am a little bit skeptical sometimes, but anyway, so that, yes.
So, so you were just talking about the issue of scale, but I would argue that are probably also very important issues in terms of diversity, particularly in terms of the work that is more related with electronic health records, right?
Yeah.
There are some public data sets and most people use them, but I mean, it's mostly English or from a single hospital or from a relatively small population. So what can be done there? I mean, is there any scaling and having larger data sets that are more diverse?
Yeah, it's a really good question. I think, like, it really does prevent progress. I mean, I think Mimic has been a really useful resource, but in some ways it's been, so Mimic is a publicly available set of electronic health records data that's been de-identified. But, you know, in some ways, I think there's like a danger in that, because it's become so dominant in this space that, like, it's all anyone uses. And like, we had a piece of work on with your former colleague, with Silvio. And so he led it, but it was basically like people had looking at like fairness in clinical predictions built on top of Mimic. And I think the issue is that if you start analyzing like your performance, like your AUC on like, different, different ethnicities or whatever. And what you see is sometimes, like, if you look at the test set, that the size of the number of test examples that have a particular ethnicity, like the number of Black individuals in the test data set in Mimic, is like really small. And consequently, if you just like change the random seed during training, you'll see like wildly different results in terms of like fairness as you might measure it, right? So like this is a problem. And then that kind of relates to what you're saying. It's more about like the size of mimic, especially when you intersect that with subgroups that are by definition minority in the data set. So I don't have a good solution to this. I don't think anybody has a good solution to this. I mean, I know that like there is like this Odyssey group, or this Odyssey kind of effort, which is trying to like standardize, but that's more about like being able to sort of exchange models, I think, as opposed to opening up data. Like there are real concerns, right? Like you can't just open up the data, but I would love for someone, medical organizations, they're just like understandably conservative by default. I've been trying to get collaborators at BWH to like, maybe we can open up like a de-identified set, like much bigger. But so far, I think the higher ups just don't see the risk assessment worth it from their perspective, So I guess the short answer is I don't know what to do about it. And it is, yeah, you're right. Like they completely lack diversity across several dimensions, and without greater access, like I don't see how we as academics are going to kind of make progress. There is a new mimic coming out that's at least going to be bigger. So I think actually part of it's already out. I think the notes aren't released yet because I think they're still like de-identifying them. So that's something, but I don't have a good answer otherwise. To be honest, it's part of why I've only kind of recently been doing more work on electronic health records, mostly because, and I don't have, I think this work in particular would probably be somewhat limited in its deployment to the local hospital that I've been working with, which is unfortunate, but like that's just the reality right now. So I guess you hope that like the methods will generalize. Like we did our experiments in that paper that in the retrieval paper, the summarization paper. We did experiments both on mimic and on private data from Brigham and Women's Hospital, which is here in Boston. Fortunately, like you get similar results for both. And the other thing that was cool is we did do an experiment where we trained using distance supervision. We trained the model on BWH and tested it on mimic and vice versa. And like you actually get pretty good, you don't get quite as good performance, but like it does transfer pretty well. So, you can sort of like do things like this, but yeah, it's not really satisfying and doesn't really address the fundamental lack of diversity. So I guess I agree with you and I don't know what to do about it.
Okay, so any other questions? Well, there's another one.
So about treating patients eligible for clinical studies, are there any work or is it still at the early stages? Because you mentioned the summarization of notes, but not that application.
So I caught most of that. So does what
work on retrieval of patients eligible for clinical trials? Do you know of more examples of work in this direction?
It's a great question. I don't know. I haven't worked on that myself, although I think it's a cool direction. I don't, off the top of my head, I don't know if anyone has deployed a system for doing that, although I hope that someone has. So I don't know, but it's very possible, and I hope so.
There's also regarding that the track challenge. I think it's still going on under a different name. So you mentioned the track competitions from 2011 and 2012, I think, but I think nowadays track still has a competition on that. They just changed the name. I don't think.
The medical. I'm sorry. Since last year, there's a track clinical trials track. There's exactly working. Like the direction is the other way. So like you have a set of, you have to match clinical trials matching to a patient.
Okay.
From patient to multiple clinical trials, but it's the same principle.
Yeah, that makes sense.
Okay, so any other questions? Okay, let's thank Byron again.
Thank you, and feel free to shoot me an email if anything comes up. And sorry for the coughing.
Okay, so well, that's it. There's going to be coffee break downstairs, and well, Byron, thanks again.
Thanks, everyone.
We'll be keeping in touch. Okay. Bye bye.